and he will talk about actual numbers and Serre's conjectures.
Okay, thank you. So first I would like to thank Peter for the invitation, and maybe it's not so common with people from Gothenburg here, but I know that Arne Berling, who was professor here, he was from Göteborg, and he even spoke Swedish with a Gothenburg accent even after he left. So it's not the first time someone from Göteborg is here. So I would like to, main purpose is to describe some results on some conjectures of Serre, not the one on Galois representations and modular forms, but other conjectures of Serre concerning the density of rational points. And then I will need some notation then, so it's convenient to use, when you look at integer points in an interval, that I denote it by set B, and then I'm interested then in the asymptotic rows of the number of integer points on an affine surface, and so I'm interested in, I look in integer points in a box such that then f of x is equal to 0. For then a polynomial, say, with rational coefficients. So everything I will do in principle extends to number fields, and Serre's conjectures often over number fields, but I will systematically work only over Q, because I have not written it up, my results, over number fields. But the method we will extend in principle without any problem. So then I think the main idea to prove, main tool to prove Serre's conjecture is a certain determinant method, and the idea is then to reduce these problems for arbitrary dimensions to problems for affine surfaces. And then to apply this determinant method. And then it's natural now to start with the result for affine curves instead, which is then started the whole business with this uniform estimates. And this theorem is due then to Bombieri and Pila. And I don't remember years very much, but I think that it was proven in 88, or it was published in 88, something like that. And this is a theorem about affine plane curves. And so, in fact, they considered also transcendental curves, but I'm only interested in algebraic varieties. So let me state it in what they proved in that case. So then they started with a polynomial in 2 variables, and this is, which is then, if this is absolutely reducible, of degree D, then they proved that n fb is then bounded. They proved the bound b 1 over d plus epsilon. So now when you, so this is a very general estimate, I mean, for arbitrary reducible polynomials. So when you see this still, you may think that maybe you are at first sight slightly disappointed, because, well, we already have the theorem maybe by Siegel, and then if it's non-rational, then you could perhaps do better. But for rational curves, certainly you can't do better. And you should notice here that these implicit constants here are uniform, and this is what makes it hard. And until this date, as far as I know, they have been, for cubic curves, there are only some very, very small, elliptic cubic curves, there are only some very minor improvements by Ellenberg and Venkatesh, where they could say maybe 0.002 or something like that. So in principle, it's very close to what is best possible that's known today. But if you assume the Riemann hypothesis for L series, things like that, of elliptic curves, then you can probably conjecturally maybe you do B epsilon, but it's another thing of really showing that. So, I mean, so, but, and as I said, for rational curves, it's really the best possible. Yeah, sorry?
For if f is defined over Q,
yes.
Irreducible is enough, it may not be absolutely irreducible.
Yes, it's enough. It's an easy case if it's irreducible and not absolutely irreducible. But when I do induction, yeah. You see, I will apply it to a higher dimension, and then it's more convenient to work with absolutely. But you are absolutely right. I can skip that, because then it lies in the singular locus, and then it's easy to control. So the way Professor Bombieri and Pila, they proved this was by using then a so-called real analytic determinant method. Determinant method. So determinant I will write like that to save time. And then there are now alternative proofs as well with a p-adic analytic. Could also with a p-adic determinant method of Heath-Brown. And it turns out that it's somewhat technical. It's somewhat, at least to me, it's simpler to apply this p-adic method. So, and the method I will present later, a global method, it's closer to this p-adic method than to the real analytic method. But I mean, this was the first method, and it's still useful in many situations. As I said, the main merit of this result is that it's uniform. And just because it's uniform, you can deduce results in higher dimensions. And what Pila did was that he applied these results by Bombieri-Pila and got the following corollary. I think it was 92 or something like that. So if then f now is an absolutely reducible, but as Professor Bombieri said, it could be afterwards you can skip this, you could treat polynomials which are irreducible but not irreducible separately, because then the rational points has to lie in a singular locus. So you can afterwards, in each case, you can weaken the assumption here. But still, systematically, I will only state all results for absolutely irreducible case. So if this is absolutely irreducible of degree d, then by just using some rather simple hyperplane plane section technique, then he got that NFB is then equal to O dn epsilon b n minus 2 plus 1 over d plus epsilon. So the proof is just you use hyperplane section and induction by dimension. And of course, for this to work, it's important that you start with an estimate which is here uniform. When you otherwise, because if you have different implicit constants, you can't really sum when you over the hyperplane sections. So let me also say then that to some extent then this is best possible, that if you take the following example here, so if you take then here that you will have that NFB is bounded from below, but b n minus 2 plus 1 over d for the following polynomial f equal to x1 d minus x2. Because then you can just use n minus 2 last variables as dummies. You can plug in anything, and then for this first two you have then this estimate here. So it's clear that if you want to prove something for all affine hypersurfaces, you can't really do anything better. But this is still, I mean, it's a good estimate, but if you want to prove Serre's conjecture, it's not, you cannot deduce a single case from this result. I mean, was for a long time the best estimate, but you don't get Serre's conjecture. So then you have to do something more. Sorry? Yeah, I will do it in 10 minutes, but I wanted to start with your stuff. So yeah, yes. So first, then I will then. So now then I will then talk about affine surfaces, because, well, here you have an example where you really have these growths, but if you exclude this kind of example, so if you exclude all cones over affine curves, maybe then you can get something better. And actually, the main theorem I will prove today, and which will imply Serre's conjectures, is the following then, that if, so S is now not for Serre this time. So if f here is a polynomial, then in 3 variables instead, And again, let's assume that it's absolutely reducible, but afterwards you can extend to arbitrary reducible case. So let's assume now that this is absolutely reducible, and I need that it's of degree at least 2. I will denote the degree by d always, and not a polynomial, of 2 linear forms, not a polynomial of 2 linear forms. Let's say then L x1, x2, x3, and then here M x1, x2, x3. So if you look at this example here, here you have one linear form, and here you have another. So this is a polynomial of 2 linear forms. So this is then does not satisfy this hypothesis here. And here, the polynomial here, all you have to exclude is polynomials over Q, the case where this polynomial is over Q and the linear forms over Q. But I do not specify that. So you exclude cones of affine cones, or cones of affine curves with vertex at infinity. If you exclude those, then you can do better here. You get then the following estimates. You get then here NFB is then here equal to O d epsilon, 1 plus epsilon here. So not 1 plus 1 over d if the d is different from 3. And for cubic affine surfaces, then I can't give any better uniform estimates. You'll see afterwards I can do some non-uniform estimates by ad hoc methods, but the best, this is in principle the best I can do in the cubic case. And I'm very pessimistic that you could prove a uniform estimate here in the cubic case and get the same result here. Basically, it's harder the lower degree you have. So if you think probabilistically, if you have, say, integral coefficients here, if you have a polynomial of high degree, then you get large numbers, and the probability, so to say, that you get 0 is smaller. So you expect that it should be harder as smaller degree you have. And of course, here, the reason you can do by d equal to 2 is that still the geometry is so simple. So this does not follow really this pattern. So the proof here is then with so-called global determinant method. So basically, it started with then the paper by Bombieri-Pila. They had a real analytic determinant method. Then Heath-Brown invented his p-adic determinant method. But here, none of those here will give you this result. So instead, I use here a global determinant method I invented. So this works for if d is equal to 3, d is cubic or higher degree. So I use ad hoc methods for d equal to 2. So it's actually not very difficult, this case, d equal to 2 ad hoc arguments. The hardest case is when d is equal to 3 or 4 and so on. So now I can proceed just as Pila did and use hyperplane sections arguments. So I could have stated general case, but I still regard this as a main result. And everything else will be corollary. So the first corollary then will then be that I just apply hyperplane sections. And then I get here the following, that if here then f is then a polynomial then with more than 3, at least 3 variables, n is absolutely irreducible of then degree d, at least 2, and not a polynomial of 2 linear forms, and not a polynomial of 2 linear forms, then I have the estimate that you expect, namely that NFB is then equal to O dn epsilon, and then I get in here bn minus 2 plus epsilon, and then if d is different from 3, and in the remaining case I get in here b n minus 3 plus 2 root over 3 plus epsilon here, if d is equal to 3. I should say here actually, I can push this slightly, so I can get here 8 over 7. I use then some theory of some problem of the Riemann. I solved the Riemann-Roch problem for non-ample device, or use some theory of some Zariski on Lazarsfeld, but I will not talk about that. So this improvement is so small and it's so much more complicated, so I will only describe this bound here. I have no idea how to go beyond 8/7. I don't see how it can be done. So this is then a consequence here. Now I should say that this result is not due to me in some special cases, so I would like to give here correct attribution here. So the case where degree is at least 6 could actually be done with the local methods. So I would like to make some remarks here. That first, this is to some extent best possible, this bound here n-2, because you will have that n f over b is bounded below by bn-2 if f is of this form x1 j plus x2 h. So this means then that you have a linear subspace of codimension 1, because then this is an accumulating subvariety. You have many rational points on that one. So you can not really get better in that case. So if you want to improve, then you have to either you have to look at the complement of linear subspace of codimension 1. Also, that the theorem and the corollary, the theorem and the corollary, it's due to a common paper by Browning and Heath-Brown and myself. Heath-Brown and myself, when d is at least 6. And there was an additional condition then that the leading form should be absolutely reducible. But I do not write that down. So, but it was not slightly less general even when d is at least 6. So that case could be handled with the p-adic methods. But the local methods does not seem to be sufficient to handle the lower degrees here. And also, even in this case, if you remove this linear subspace of codimension 1, then you get stronger result with the global method than the local method. So to some extent, it's as soon as the dimension is higher than 1, the global method seems to be slightly more powerful than the local methods. I mean, the improvements are not enormous, but they are still decisive. I mean, it's thanks to those improvements you can prove, I mean, these conjectures by Serre, which I will state in a few seconds. So now, let me also say that you may then ask, is this desperate then? Can't we prove anything for cubic hypersurface? Well, this determinant method, which I will describe, is very good when you have forms of polynomials of high degree and you have singular things. Then it's superior to the circle method. But there is the traditional then hard little circle methods. It gives better results when you have smooth varieties, I mean, defined by polynomials of low degree. So for cubic forms, you can all try to do the circle method. Then there is a problem that the well-known harder little circle method, it does not give uniform constants here, but you can apply, so to say, discrete versions of it. And this was done by Heath-Brown, and then he proved here this bound here when the codimension of a cubic hypersurface, single locus is of codimension at least 9. And then I improved that to 6. So if you have a cubic hypersurface which is not very singular, then you can still prove it. But those methods really require estimates of the linear, and then you cannot have, the hypersurface could not be too singular for this method to work. So I will not explain any results today based on exponential sums, but you should know that this determinant method I will explain is not always the best one. In some cases, there are other methods which could be used. So now then, the time has come finally to formulate this Serre's conjecture, and then I have to decide what I will keep. Well, I will keep that main theorem. And then I will still erase this, but this conjecture here will implies, okay, I can keep it for a while, because I will use that one to deduce Serre's conjecture. This one I will not need anymore. So here are then Serre's conjecture. Those conjectures, they were probably formulated in his lectures at Collège de France. It was before I spent some time in Paris, but not that so early. It was in the 80s, but they appeared. There was a book in lectures on model Weyl theorem. So it's a grey book on model Weyl theorem, and it's in Viehweg Verlag. So if you will find all those conjectures, I will formulate now there. So the first of his conjecture, I will call it the dimension growth conjecture. So he formulated it for number fields, but I will only do, as I said, the case over Q. So let then here x of Pn of Q be an absolutely irreducible variety. And again, you can extend it to reducible variety, which are not absolutely reducible. But for simplicity, I will only discuss this case of degree at least 2. And then I will consider then the following counting function. So I will count all rational points on this projective variety, which is of bounded height, such that the height is at most b. And the height is a very naive one. You just represent each n+1 tuple in Pn by primitive n+1 tuple of integers, and then you just take the absolute value of the biggest one. So it's a naive exponential height. His conjecture then was the following, that the growth of this, asymptotic growth of this, should then be equal then to O x epsilon b, and then you have the dimension. It should grow like the dimension plus epsilon here. So in fact, he formulated slightly stronger that with a log factor here. I did not say it, but for instance, in this result by Bombieri-Pila, I could replace it b epsilon by log b. So, but in high dimensions, I don't know really how to do that, except in cases where you have some smoothness assumptions. So I will formulate Serre's conjecture in a slightly weaker version, but still the important here is the growth order. This is really the important aspect of Serre's conjecture. So it's a slight weakening on the version in his book. So this is then first conjecture, and I should say also that this was conjectured by Heath-Brown for hypersurface before Serre's conjectured by Heath-Brown in 83, in fact, for hypersurface, but in 1983 for hypersurface. And this was in his famous paper on non-singular cubic forms in 10 variables, where he proved that each such form has a non-trivial zero using the circle method for hypersurfaces. And actually, he did it over Q, and Serre extended to arbitrary variety, and he also extended it to arbitrary number fields. But I only stated for Q here. And then there is a second conjecture in his book, which imply this one. They're so-called thin subsets. And now you can find anything on Wikipedia, and I noticed that there is an article in Wikipedia about thin subsets. So if you want to know what it is, you just go to Wikipedia. So, yes. So I will tell you indirectly what it is. So now, instead of looking at sub-varieties, we will look at covers now. So we will have then a finite dominant map. So let then here x p of pr be a cover of degree d at least 2 over q then. So both are defined over q. But as I said, so I did everything over number fields with then x absolutely reducible X absolutely reducible. Then you have the same growth order here. So then if you count then the number of rational points, such that then the height of the image here is at most b. Then this should have the same kind of growth behavior, b dmx plus epsilon here. Again, he had a log factor here instead. So then what did Serre then prove? Well, first he noticed that this second conjecture implies the first conjecture. So we have then that the second conjecture implies the first conjecture. So, and then he obtained the bound. He obtained then the bound. He used then the large sieve, large sieve of Linux, and then he proved the following bound in this book. Serre proved then the general bound. So he had then here O x epsilon, and he had then b dimension of x plus 1/2 plus epsilon. And in fact, he used then the large sieve, and in principle he followed and he attributes it to also to some extent to Cohen. So it's just that I have to confess I found this presentation by Serre so brilliant, so I have never looked at the original paper by Cohen. So, but he quotes Cohen. So I think Cohen only did it over Q. So Serre does it develops a large sieve over arbitrary number field. So now, but this bound was then beaten by this result of Pila, because Pila, he also noticed that in this theorem I stated in the beginning on affine hypersurface, from that you can obtain general results on projective varieties. So what Pila did then in the same, is some volume in asterisk, some number series seminar at Columbia University or something like that. So there is a report by Pila, and then he proved that if then here x of Pn is absolutely reducible of degree d, then he proved that this counting function, it grows then like and this is uniform then. So b dimension of x plus 1/d plus epsilon. So and this is of course true even if d is 1 here. So Serre proved the general if d is 2, of course, the degree here, because it's false if you have a linear subvariety. But if you compare those, you see that d is at least 2, then this is 1/2. So it's just as good. And as long as if d is bigger than, so degree higher than 2, then this estimate by Pila is better than Serre's book. So this estimate is widely quoted, for instance, in a book by André Silverman. I mean, they quote this result. So this was for a long time the best known general bound for an arbitrary variety. But then rather recently now it has been beaten, and by using, consequence of this result here, so then we have the following result. First, so this is 2006, and after that, so we have then here that if then here x now is a projective variety here, if this is absolutely reducible again, of degree at least 2, of degree d at least 2, then you have that nxb is equal to ODN epsilon. So it's exactly the same bound as you saw before for affine hypersurface, so you will recognize it. If the
conjecture 1 or conjecture 2 here?
Sorry?
So when Serre shows that 2 implies 1, Serre proves that for 2, I assume, not for 1.
Yes, he proved this bound for 2, yes, and then he just notices.
From now on, you'll talk about 2 all the time?
No, I will make that clear. So here is conjecture 1, and I will also state my results for conjecture 2. So basically, I can prove conjecture 1 in all cases, but I cannot prove conjecture 2 in all cases. So for instance, if you take d is equal to 2, then the conjecture 1 is just about quadrics. But conjecture 2 is about double covers over Pn, which is a much larger class. So it's really much harder to do that than to do. But I think it will be clear after I have finished, stating all the results here. So this is conjecture 1. That I can prove then if D is different from 3 here in a uniform way. So I have then this uniform estimates here, B dimension of X, plus then here minus 1 plus 2 over root of 3. I hope I got it right. Yes, plus epsilon here. If then D is equal to 3. And the truth is that I can do a little bit better here. So I can push this to plus 1/7 here. But I have not written that down, so I prefer to state what I have written down here. So this result here, so it's complicated to attribute everything. Let me just say orally that this is due to Browning, Heath-Brown, and myself. I have to correct it. So this theorem here is due to Browning, Heath-Brown, and myself in case D is equal to 6, and it's due to Heath-Brown if D is equal to 2. So this was included in a great paper in Annals of Mathematics in 2002, but this is one of the easier results. So in that paper he developed the p-adic determinant method. This first result was in a paper in Duke 2006. And finally then it is due to myself then if D is equal to 3, 4, or 5. So actually I tend to think that these cases are harder, as I said before. So then it's still disappointing in some ways. I was frustrated that I could not handle it completely because it's very annoying. You could prove a conjecture in all cases except one. So what happened was then that I finally realized it's impossible to use the determinant method here. And I was obsessed with this uniformity. But after all, Serre, he did not require uniform bounds. So why not instead try to develop another method which gives non-uniform bounds? And for cubic hypersurfaces, in fact, I was then able a few months ago to develop some completely different methods to prove Serre's conjecture in that case as well. So I can prove, but not with uniform bounds. So at the end of 2010, then I proved that if then here x and Pn of Q just absolutely reducible of degree D at least 2, then I have at least a Serre's conjecture in general, but not with this extra uniformness in the implicit constant. But still it's Serre's conjecture. So it's now then known in general. And this is then the first conjecture here, the dimension growth conjecture. So this is now known for all varieties of degree 2, at least 2. It's of course false for linear subvarieties. Then you get growth order +1 here. The second conjecture, however, is not known in all cases. So let me state what, and this I also did last year. I lectured about it in Zurich conference here. This first is written down. Second one is not yet written down. But it's proven by similar methods, but it's a little bit more complicated. So if this is a cover of degree D, then you have this counting function. So I don't know if I have to write that. Let me just call this NXB here to save time. This is really an abuse of notation, but I think just understand what I mean. NXB is then equal then here to O. And this will then depend on X, and it will also depend on the morphism here. So this is, well, let me write it like this. B dimension of X plus epsilon. I can prove this if the cover is of degree at least 4. But in the other, if the degree is at most 4, then I get then here B dimension of X plus minus 1 plus 2 root over D plus epsilon. D is at most 4. So if you look at this, for instance, with D is equal to 2, then you get root of 2 here. So it's still better than Serre's large sieve bound, even for double covers. So this is still open for covers of degree 2 and 3. I should say that, again, if you have something very smooth, you have some chance of applying then exponential sums. And there is a sieve which is more refined than large sieve, which is a Heath-Brown square sieve. And I know that Rita Brata-Munchi, I think he's a student of Wiles, he's come from Princeton as well. He has some results here, but he has not been able to prove Serre's conjecture. But I think now that Lillian Pierce, I think she's also from Princeton, she's working with Heath-Brown now in Oxford, and I think she might have some results that he applies Heath-Brown's method, his square sieve. But the problem is that you will then need very subtle applications of a while too. So you know what you expect, which should be the relevant bound for the exponential sums, but still maybe you have to write to cuts to get the proof. You have to use some perverse sheaves or something like that. So it's more the exponential, but there are other methods for double covers in case you have something which is not too singular. So it's an interesting area of research to study this for double covers and covers of degree 3. So now I think I've stated all the results. And so I should maybe say then something about the proofs here. So this is a rather straightforward method deduction from these result for a fine hypersurface. It's just that if you have a projective, you just have some birational projection here onto a projective hypersurface. And you can then control the heights, compare with the projective hypersurface. If it's birational, it will be of the same degree. So there is an easy reduction here to projective hypersurfaces. And then you can just look at the fine cone and apply this previous result for a fine hypersurface. Here it's more complicated to use a birational projection argument. You have to prove a birational projection onto weighted hypersurface. And then again, the induction hyperplane section argument is also more complicated. You have to destroy the homogeneity, and then you still have some weights you have to consider. But the extra difficulties are geometrical rather than arithmetical here. But you cannot deduce this result from the previous one. And you cannot get any uniformity here. Half of the proof is uniform, but some parts are not uniform. But the determinant method is used here as well. Okay, so what I will do now next is that I will discuss, this main theorem and the determinant method. So it seems that I have only 20 minutes, but I have to use them well then this 20 minutes. Actually, I think we started at 32 or so maybe I have 22 minutes, so maybe this will help. So now I will not talk about Serre's conjecture anymore. I will just talk about the fine surface and the determinant method. And I regard this as the deepest part of the proof of Serre's first conjecture. At first, it was not even clear that it can exist a global determinant method. So I will explain to you the difficulty. So basically what I do is that I use congruences modulo all primes at the same time. But to prove that you have a lot of p power factors in a certain determinant. So this, and then if you have an integer with many p factors and it's bounded, then it has to be 0 if these factors are high. So this is the idea. So I would like then first to describe then this determinant method, and this can also be used for projective hypersurface, but I will now describe it only what I need here. So the determinant method, and let me then state the theorem, which is then essentially due to Heath-Brown, but he proved it. But it's here you see. In this proof, still, it's not completely enough to work only with hypersurface. You also sometimes need to work with arbitrary varieties. So let me state this in a somewhat more general situation than Heath-Brown did. So let then this be an absolutely irreducible algebraic subvariety of dimension R and degree D. And then again, so then I will then introduce then a notation here. So I will then introduce this notation here. So this will then, I have then here the set of all Q points here. It's part of then Qn, and in Qn you have also Zn. So, and then you can intersect this with minus, or you can intersect it with set Bn if you want. So this is then the definition. And if you don't like this, you can just take a scheme theoretical closure here, and then you just look at set point on this scheme of a set, and then these integral points should then lie inside this box. So this is another way of looking at it. And then the result is the following. Then there exists for any epsilon an auxiliary polynomial j, which then belongs to q, x1, xn, not vanishing on this variety, not vanishing on y, of degree. And here you will recognize this exponent of Bombieri-Pila. It's just that it's for arbitrary dimension here. So this will be b r over r's root of d now plus epsilon. So if you take r equal to 1, then you get 1 over d. So all of whose irreducible factors, are of degree, are of bounded degree here, are of degree, you have then here O, d, n, epsilon. So they are uniformly bounded, I mean all the factors of this polynomial. And this supplementary, this auxiliary polynomial, it will vanish then on all those integral points inside this box for all y belonging to yz of b here. So let me then give you again an attribution here. So this is due to Bombieri-Pila. I just write BP now since I'm short of time. R equals to n for plane curves. And it's due to Pila if for arbitrary curves, not just in A2. And then Heath-Brown, he wrote an important paper which really made an advance of this determinant method. He transformed it into a p-adic method. And then he was able to extend it to higher dimensions. So Heath-Brown, he did it for hypersurfaces and then I have various students who have extended this to arbitrary varieties here. So in general, simply then n are bigger here. So, and then I have another student, Marmon, who reproved this again. So these papers here are p-adic. And then my student Marmon, he extended then now the approach by Bombieri-Pila, so it can also be used to prove this result here. I should say also that he did it just like Bombieri-Pila. It works also for real polynomials here. So in this version here, you can just assume that this is a variety in over the reals, and you get the same results. So I should say that after this paper was written by Bombieri-Pila, then Pila himself, he noticed there is a very powerful theorem of Gromov, which can be used to get nice parametrizations. So the reason it's easier now to apply this method of Bombieri-Pila is that you have this powerful result of Gromov. So this is, he strongly uses that. And he also had discussed with Pila, got some help from him. I will then still now, just to present the determinant method, the p-adic version. So this is a local result. It's not enough for this theorem, but before I can describe my own result, I have to present this result because I will build upon this result and refine it. So proof then So then after Heath-Brown then. I mean, he did it only over hypersurface, but I mean, all the main ideas are due to him. So what he did then was that he reduced it to what Bombieri-Pila, they divided it into small neighborhoods, into small partition, into small patches, I mean, of real analytic patch. But Heath-Brown, he divided into p-adic boxes. And so let us then fix one point here, P, which is then non-singular point modulo P. Of course, this is not well defined if you start with a variety over Q, but you can just take the scheme theoretic closure, and then it has a meaning then, this variety over P, over field of P elements. And I will assume now that this reduction modulo P is non-singular. And this will require, for this argument to work, it will require that P is at least then B1 over R's root of D plus epsilon. And then the implicit constant here, this will be depend only on D, N, and epsilon. So the reason I put this at the end is that it's a little bit technical. Already in this first results here are already quite technical. So I will try to be as not so technical here. So you look at, you count first elements, you divide have a division into partition into p-adic boxes, and so then you look at all those points in here in this box, integral points, which then specializes to this given point, P. And then I have then to take the union over all those residue classes modulo P. Now there is a trick here, which due to Heath-Brown, which tells you that you may really assume that that it's enough to find a auxiliary polynomial for this set. So, and I will explain that. So by then Siegel's lemma, then it's enough to find a polynomial h of q of x1 to xn of now not of degree m, but I will now, this will correspond to these factors. Find h of degree O, D, N, epsilon of 1. So it will be uniformly bound. It will only depend on these three parameters, which vanishes on this set, which is equal to 0 on this set in this box, but with this congruence condition, but not on this variety, but not on y. So then, if you have such an auxiliary polynomial, if you want to count an element in this class, then you can just take the intersection with this new hypersurface and you reduce to a problem in lower dimension. And then you can proceed in this way by induction. So how can you just reduce to a non-singular classes? Well, let's first note that for the singular points, it's easy to produce such an auxiliary polynomial. You just look at Jacobi, you just look at the derivatives, and you immediately then something polynomial has to be 0 bounded degree. So it's enough to study non-singular points over Q. And what this Siegel's theorem does is that, let me just explain that you may then assume that the coefficients of the polynomials which define y are of polynomial order. So let's take this for a linear form. Suppose now that y is just a hyperplane. So either then it's spanned by the rational points of height at most b, and then you just look at the determinants, and then you immediately see that the coefficients of these linear forms is of polynomial order. Or it's not spanned by this point here, but then you have another linear form. And this simple argument, you can extend it by Veronese embeddings or even by systems of polynomials. So you may assume by Siegel's lemma that the coefficients of the polynomials defining y are of polynomial order. And once you have that, then it's clear that the non-singular points has to reduce to non-singular points for a small set of p. So you have to use more than one p, but it's sufficient to do it for a very small number of p. So you may pretend that this variety has good reduction. It's non-singular good reduction at all p, and the general case is not harder. So we are now faced with this problem here. This is all we have to do. And the idea now is to, just I'm running out of time, so I have to make some cancellations here. Sorry?
We are flexible with time.
Yeah, okay, but I will really try to make an effort here. So, so choose now here a maximal set of monomials f1, fs in these variables here, x1, xn, of bounded degree. Because I will produce, I want to produce a new polynomial, and this will then be a linear combination of these monomials. And then the monomials, they will all be of certain bounded degree, and I will tell you afterwards what the bound is. And I want them to be linearly independent modulo the ideal which defines this variety, such that whenever you take, if a linear combination here is 0, this should then be possible on y only if all coefficients are 0 here. So I want all any nonlinear trivial combination should not vanish on y. So I choose such a set of monomials, and I will tell you later what u is. I can't do it at this stage here. So now you may compactify this y and to something in Pn, and then if you want to count all the monomials of degree at most u, it's then the same as counting the forms of degree u in P on the compactified variety, and then you can relate this to Hilbert polynomials. So by comparing now with Hilbert polynomials, so here I have to assume you know some brachiometry, but we are at Princeton, so I think it should not be any problem. Hilbert polynomial here for compactification, then here x in Pn of then this y in An. Then one gets in here that the number of such monomials you can then get that this is roughly thendur divided by r faculties. So it just corresponds to the Hilbert polynomial of this compactification here. So you can find that many monomials of degree at most u such that they are linearly independent in this way here. So now the next thing is that we also have equations in y. And now what I want then is that I want to have them as low degree as possible. So if I have an equation, I can always try to get rid of some x here and put the 1 instead. So if you look at the homogeneous version with x0, x1, xn, then you want to have as many x0 as possible. And basically what you can do by some Gröbner basis technique here is that you may choose this f1 fs with average degree at most then r divided by r plus 1 of u. So the easiest way to understand this is that so r is then here the dimension of y. So let's think about the case of a hypersurface, a defined hypersurface. Then you have r plus 1 variables. Then you can always arrange such that the first new variable then in this compactification occur at least as many times as the other ones. So this is just an heuristical description. I mean, the actual technical work is harder. So now we can just use a definition of a determinant, form the relevant determinant here. So at least I will have the time now to write down this determinant I will consider. So the determinant here is that the following here. So then I can estimate this determinant here. I will then get then here f1 y1 f1 ys. So I take then here fs y1 fs ys. So this will then be satisfy then b. So these are the number of terms. So I will then let here. So I will call this number of these are the number of monomials is s. and S, the number of monomials, is then DUR over R faculty, and the average degree here is R plus 1 of U. So if I evaluate this determinant in at points inside this box, and I will always have at most B here at each term. So this is for Y1, YS, which then belongs to this Y set of B. So I don't need these congruence conditions here. So this is just by the definition of the determinant. And the idea now is that I will now produce I will now show that this integer is divisible by a P which is higher than this bound here by using these congruences here. And I have to really decide now if I should do this. I think it will take me 5 minutes and you will just get, so maybe I skip this part, so I just write down. Can do it? Yeah, okay, sorry. So if you have already had 3 hours with the previous layer, which were really, then maybe I thought it was too much for you, but okay. Yes. So let me then tell you, because this is at least the main idea. So this is a local p-adic method then. So we also have to show then that this determinant is divisible by a power of p here. So in that case, to study then here p e factors of this determinant here in then set p. Then since I'm not interested in the size, I'm only interested in factors of p, I can make linear coordinate changes over set p and arrange everything such that it becomes nice. And after suitable coordinate changes, I just want to give the idea, I mean the coordinate changes are not hard to make, over then set p, then we may assume that, this first point here is 0, 0, so that this is the origin here. So then it's much easier then to evaluate if we know that the other ones are congruent to this one, then they will always have coordinates divisible by p, and then it's easier to produce p factors here. So it's going to let me just state this. The next thing is then that I can want to apply then the implicit function theorem, and I want then the last, if this is of dimension r of n, I want the last r, n minus r, to be power series of the first r ones, and this can then be achieved by I use then here the fact that I have a good reduction, so I can also assume that the last variables here in an, I can assume that they are formal power series of the first r here, xr. So this is then very convenient, because then all these monomials, they will then be expressed in terms of the first r coordinates, where r is the whole time will denote the dimension of this variety here. So note that this is an arbitrary variety, it's not just on hypersurface here. So now I have a very good tools, to study these p factors. Now I have then here power series. So all those here are now power series. And then I can use elementary transformations to, the whole time I want to then to get rid of those terms of low degree, because they will then prevent me from having good p factors here. So after now elementary transformations and here, after then here elementary transformations and here, in then here f1, fs, we get then here at most r plus k plus 1 minus k elements in. So what is this? Well, let's call this ring R, and let's call then this is then a local ring. So let's call then the radical then. So then it has a natural maximal ideals here. So I can then call this J. So let me call this J is then here the maximal ideal here. This is then the maximal ideal here, Jacobson radical or whatever. So you can arrange such that you have at most that many elements in delta, because otherwise you just continue to make, because these are the number of this is dimension of the quotient of this vector space here. So you can always, by just linear algebra, you can just arrange such as you have this, and then you will have that many, elements here, that many rows divisible by P of k. So you see that the p factors here will be higher and higher just using this elimination process here. So now what we get out of all this is that we get the following p factor. If we just sum then over, we know exactly how many p factors we have of each degree here. So then we get a lower bound for the p factors here. So what we get out of this is then the following here. So hence, what I will get here is that I will get that PE will divide delta, where then this E is then isomorphic to approximately VR plus 1 divided by R minus 1 faculty divided by R plus 1. And this comes then for such a sum here. R plus K minus 1 over K here, where K is smaller than V. And what is V? Well, you have then here that VR divided by R faculty is isomorphic to du R divided by R faculty. So this is a number of monomials you have. So this corresponds to the number of power series you have. And then by using where they are in this filtration, you get this expression here. So basically then V is equal to the R's root of D times U. So here is where this R's root come in. This is when you study these P factors. So now we can compare then this, we can now compare this Archimedean bound with the P power factor here. And then we get then here the following comparison then here, such that if now this P factor is bigger than the bound, Archimedean bound, then the determinant is 0. Then this determinant is 0 if then roughly. So the actual computations are even a bit more harder because you have to control all error terms, but in principle it's not difficult, it's just some bookkeeping. So you have then here DUR over then here R minus 1 faculty, R plus 1. This should be bigger than B. And then you get then here du R plus 1 divided by R minus 1 faculty, R plus 1. So this is a condition you need. So what's that? So this is, well, it comes down to, miraculously, it's just that if P is bigger than B, and then you have 1 over D1 roots of R. And then here you need some B epsilon to control error terms. So this is how you prove that this determinant is 0. And if this determinant is 0, then some linear combination of this F1, Fs will now vanish at this, all those set in this p-adic box. So this is how Heath-Brown proved this. And then what I have done is now an extension of this. So if you look at this bound here, then you have then here that this auxiliary polynomial is of degree R over R's root of but in fact, using a global version of this determinant method, then I can replace this R by 1 over R's root of D for the total auxiliary polynomial. So this is much lower degree. So I have the following theorem, which is then proved by looking at all congruences, not just at one modulo 1 prime P. So let then here Y in AN of Q be an absolutely irreducible variety of dimension R and degree D. then there exists for any epsilon, then there exists for any epsilon a polynomial j, which then belongs to this polynomial in these variables, not equal to y on, not vanishing everywhere on y, of then degree O dn epsilon be 1 over r's root of d plus epsilon with j of y equal to 0 for all y in y set of b. So when I found this result, I was very happy because, for instance, if you have an affine surface, for instance, if you have y in A3, if this is in Q, and if this is y then a surface, then here you get then here that j is n of degree O b 1 over root of d instead of, as before, O b over 2 over root of d. So there is some epsilon here, of course, as well. So this looks to seem to be then a much more powerful result. But there is one problem here, and this is that here you have a very strict division into boxes, a partition into boxes. So in each box, you have that the auxiliary polynomial is of degree O of 1. It does not depend on b. But here, this new polynomial will be of depend on b. And this makes it very hard to iterate. So this theorem can be iterated. You can proceed by induction by dimension. But here you can't iterate because then you have to control of the, you have to know how this implicit constant depends on d. And if you try to solve this for curves, now what you would need to succeed here is that you would need to, that it depends like d square, this implicit constant. And no one has been able to prove that. So the best we could do is maybe d4 or maybe d3 or so, but it's still completely insufficient. So it seemed for a long time that this theorem, which looks so powerful, it turned out in fact to be absolutely useless. So in spite of the fact that you use more information about all congruences. So I was stuck for 2 years or so, and no one else saw how to knew how to continue. But then I found a way out, and this is really one of the things I'm really proud of in my mathematical career. And this is that what I did was the following, that I used the whole spectrum of interpolations between this theorem and this theorem. So I do not just apply the global and local methods, I imply all this interpolation at the same time. So this first result, it's true, you could replace p by a product by a square-free number. So what you do is that you replace p by a product of the smallest number primes you have at your disposal. And now you get then a division into a small number of boxes, because if p is 2, you get very few boxes here. But then you take maybe 6, and then you take modulo 30, modulo 210, and so on. So you get more and more boxes. And for each such square-free number, you get some interpolation between those two theorems here. And now what you do is that you look what happens with all those auxiliary hypersurfaces. So here you have something of low total degree, but and then you look at all the irreducible components here when you cut with the variety. And then you see what happens with the next one. And finally, at some, there is a dichotomy. Either there is a break, either you will at one stage get a new hypersurface, and then you can deduce a Bezout argument, so you can produce something of codimension 2, or you will never get a new irreducible component. You will go through the whole way until you are here. And in that case, you get then 1 over root of d curves. So what you get finally with this method is that you get that it's covered by a certain small number of hypersurfaces, or a certain small number of codimension 2 varieties. So this is what you can do. But still, this makes a whole difference. So you can then apply such a result that you can cover it by subvarieties of codimension 1 and 2, and then at each concrete variety of dimension more than 1, where you have some result with the p-adic determinant method, I can always get something slightly better with this new determinant method. And this was made the difference to prove these results by Serre. And just to illustrate the difference between what you can do with Heath-Brown's method and this new global method, I would just like to state one more result. Instead of explaining the proof of this main theorem, let me just state one more result. So you see that sometimes the difference is very small, but still there is a difference. So because you can also apply this to many special system of equations, I mean, some of them are important in analytic number theory. For instance, if you want to look at class numbers of imaginary quadratic fields, if you want to estimate the torsion, it gives you a Diophantine equation. Sometimes, if you want to have zero-free regions of Riemann zeta function, your Vinogradov's method also depends on Diophantine estimates. And you can look at the papers of Heath-Brown, you will find many interesting applications of various Diophantine estimates. So yes, me just state one theorem here. So let then here f then here be equal to a0 x0 d plus a1 x1 d plus a3 x1 d. So it's on a quaternary form of degree d with then here a0, a1, a2, a3 different from 0. So these are all rational numbers here. Then you would like to count all the solutions here in a box. So then the number of solutions to the following equation, f equal to 0, and then I don't want to, there are some obvious lines here which are accumulating subvarieties. So let me then also demand here that I don't want to be on any of those lines. So if d is equal to 3, you have 27 lines, for instance. And those 27 lines are then given by those, that any one of those should be 0. So let's assume that I have as well that those are different from 0. So then I take the complement to 3 d² lines. So let's then count in then set B. So I'm interested then in integral solutions inside this box. Then this is then equal to O d epsilon b 3 over root of d plus epsilon. So this is then my bound here. If you compare this with Heath-Brown's result, which he obtained with the p-adic determinant method, then he got something which was almost as good. It was just slightly bigger, so he got then 2 over d minus 1 plus epsilon here. So of course, if d here is 1 million, I can't say that my bound is so, the improvement is so big, but say if d is equal to 5, then still there is some difference. I mean, this bound here is better. So this is very typical of what happens if you replace Heath-Brown's determinant, p-adic determinant method, or Bombieri's determinant, Bombieri-Pila method with these global ones. You get something slightly better. But sometimes this could be decisive, and this was helped me to prove the conjectures of Serre. So, okay, I'm sorry that I have overrun my time.